Yeah, so I wanted to carry on in the theme, maybe, a little bit, of Blaise's talk from last week, in which she discussed their project they have with various co-authors about through studying ordered abelian groups, trying to understand exactly when it is that, or what kind of property of K, little field, and this, I think they were working in characteristic zero, really, last week, is that all henselian valuation rings O with residue field K, and maybe I mean elementarily equivalent to K, or maybe I don't, that's part of the kind of question. All henselian valuation rings with residue field blah are let's say zero definable inside their fields of fractions. And I mean in the language of rings. That's a question. What kind of property of a field is that? And the rough answer from Blaise's talk it should be that little k is not C henselian, meaning is not elementarily equivalent to any k star that admits non-trivial henselian valuation. At least one direction of this is very easy because, as Blaise explained last week, if just a kind of a little remark or a little discussion, if V is a non-trivial henselian valuation on K. I don't want to say no. Oh no, sorry, I think I want to go the other way around. My bad. So I want to go the other way around. Suppose you have one field K with two henselian valuations. V1, V2 with residue field little k1, little k2. Then, unless something's separately closed, you're going to have something like V1 corsons V2, and so in particular that would mean that K1 admits a non-trivial henselian valuation. If you don't have some kind of uniqueness always of such valuations inside on their field, somehow inside the space of valuations on their field of fractions, then you must obtain this property, not being of being elementarily equivalent to a field of that non-trivial henselian valuation. And this uniqueness, by the Beth argument that Blaise discussed last week, is essentially the same thing as being zero definable.
Why is it true that one has to be a coarsening of the other one?
Well, the tree of henselian valuations, if you want to call it a tree, which is a bit fast and loose, that's the sino direction, that's the coarser direction. All these ones here, which are not in a total order, have separately closed residue field.
Okay. Well,
So I'm just saying that there's a couple of cases one should think about, but basically one can imagine one's here. So I just wanted to kind of put in place a reminder of a fragment of last week's discussion. And now I want to tell you a similar story. Around existential formulas. Existentially definable valuations, henselian valuations. Okay, so let me begin properly. So, just as a brief reminder, I'm very, very interested in this kind of field, these power series fields, which are, as sets of things, they are sets of formal sums like this, and I should probably go from some integer n to infinity, and of course once you think about what the addition is, it's just term by term, and what's the multiplication? It's the kind of usual product you would take of series, so t7 times t3 is t to the 10.
oh, sorry, can I ask one question?
Yeah.
So is that when the definition of T henselian, is it exactly what you wrote there?
Exactly. Let's say yes. There are several equivalences, but that's as good as any.
So it is equivalent to that.
Yeah.
Okay.
Yeah.
Yeah, I mean, I guess because the English is weird, any needs to turn to some. I mean, this is confusing, I think.
Oh, I see what you mean. Okay.
Yeah.
So it means that T henselian, you mean there exists
Yes.
a field K star elementary equivalent.
Yeah, I think I meant. Yeah, I was saying. I meant to say not. It's not the case that any A star elementary equivalent admits an non-triviality variation. Thank you. Caution.
So the definition of T henselian means there exists one field.
Exactly.
At least one field K star.
That's a very good point. Thank you.
Okay.
Every, any, all, and negating them, it gets very confusing. Okay. All right. So the kind of the question I really want to focus on then, so like today's question, is when is f square bracket t, which is the valuation ring inside here with respect to the t-adic valuation, that returns the most appropriate choice of n for any series here, that is the least I such that ai is non-zero, and this is the valuation ring with respect to that, when is this existentially zero definable in its field of fractions? So I just mean without any extra parameters allowed in the formula. So really a formula which might as well be of the shape there exists y1, there exists yn, such that some other thing is true, and that this should not involve any, that's quantifier free, should not involve any quantifiers, and it's in the language of rings, so basically it's some polynomial equalities and inequalities, and we could simplify it further if we cared to, yes.
So how do we talk about like the range of the valuation? Because that's like the valuation is supposed to spit out a number. Do we just associate that to one that many times in f of t?
Do we associate that to, sorry, one?
So if we're talking, I guess, how do we talk about what the valuation equals in our language? Because like those objects are not numbers a priori, and especially if we're not in characteristic 0, how do we like talk about that?
Yeah, fair point. So I'm just assuming you're not asking this in a kind of logic sense, like what sort are we in?
I guess I'm asking, are we two sorted?
Well, I actually don't really care for this purpose because I'm just interested in when is this valuation definable using formula from the ring.
Oh, so when is it? Okay, so we can't just.
But it's a really important question because it does in fact play into the discussion a little bit, which is what does it really mean that two valued fields are elementarily equivalent? And for today, it's fine to think, if you want to, of the valued field language just being the ring language with an extra unary predicate. So this doesn't quite answer your question, but so for today's purposes, it's fine to say that a valued field is essentially just a field with a distinguished special subring that happens to be a valuation ring.
And that predicate is what we're trying to build with just universal quantifiers?
Yeah,
Okay.
With existential quantifiers.
Yeah.
However, let me also make the side point that how do we view the actual values? Well, then I suppose they're just elements of k times mod O times, in a sense. Or they could be any element of any group that is the value group of an evaluation that's equivalent to the obvious one here.
Okay, but those
And
values,
it doesn't matter.
yeah, those values don't show up in our formulas, so we don't care.
Oh, exactly.
That's also, sorry, I don't want to.
Let's go for it.
Okay, so the original question you asked, I'm trying to understand how it relates to the remark you made. Is it possible that you could have a field with residue field k? You could have a field that has two different henselian valuations, and they're both zero definable.
That certainly can happen.
Okay.
However,
there are examples of that.
Did you say henselian?
Yeah.
Yeah. All right. How about so this is sort of beyond question as opposed to as a remark. How about the field of fraction of the ring of width vectors of SDT? I haven't convinced you of this yet, but let me just now draw a picture. So what kind of henselian valuations does this field admit? Well, it admits the trivial one.
The fraction field.
The fraction field of the ring of weight vectors. Yeah.
Okay.
If you prefer to write frac, that's fine with that.
I think you need to be slightly careful because what you've written down is not perfect.
Oh, thanks. No. Thank you. So there's the trivial one. There's the p-adic one, which has as residue field this thing. I mean, it's p-adic in the sense that it has p as a uniformizer. And then there's the composition of that one with the t-adic one here, which I suppose we could still call t-adic. Now, I haven't convinced you of this yet, probably, but in fact, all three of these are zero definable.
Okay. I guess they have different residue fields, but
They certainly have different residue fields. And did you ask for one with the same residue
well,
field?
I didn't move it.
Probably not. Also fine. How about? Oh gosh.
Okay, maybe I don't want to derail it.
Yeah. Okay. I suppose.
I'm just trying to understand.
Challenge
I'm just trying to understand the logical relationship between the original question and the remark you gave.
Yeah. Well, because the question was posed, when is it the case that all of these things should be definable? It would naturally follow by compactness that there would have to be a uniform definition, and one formula cannot define two things in the same field. Cannot define two different things in the same field. So it sort of necessitates that there's only one such valuation on each. That's the link.
Wait, what do you say? Why couldn't you have two different? I think you just
if a k, little k falls into this class, it necessitates that big K's can only have one henselian valuation with residue field such a little k.
Well,
It's just because
you get two. Otherwise, you could take like an alter product of them and get
and then
uncountably many.
You'd still be in a setting where some formula ought to work, and so there's one formula that should work for the whole class.
Well, why must there be one formula that works?
That's just a compactness phenomenon.
Okay, yeah, that's okay. So, okay. Good.
Okay. At least what I'm saying is, I tell you what, let's just move on.
Yeah, let's move on.
I'll happily come back and discuss it a bit more later. Okay. So what's the answer? What's the answer? When is this existentially zero definable? So this is any answer is obviously a property of, or a property only of, if you see what I mean, depends only upon, right, it's a property of f. Just because this object only depends on it. So I'm not saying anything clever. But it's actually depends only on the theory of f. That's a bit less obvious. Why is that? Well, it's not hard to see. That f and f star have the same existential theory. What do I mean some existential theory? What am I trying to say now? Yeah. Building on this.
F star is any field
Yeah,
element
yeah,
reactor. Equivalent, yeah.
Okay, building on this kind of thing, building on this kind of thing, building on this kind of thing, one sees easily that sorry, a little bit out of order. Yeah. Sorry. Let me just start a different sentence. So I want to tell you exactly what property of this theory it is. That's what I want to know. Okay, so let's have a few kind of little examples.
Can I ask one more question? So in the original question, if the answer is yes, then as you said, there must be just a unique henselian valuation ring inside. Is that right? Inside any field there. What was the statement? Is there every?
Yeah, I guess I'm really saying if all such O's are definable, then they're uniformly definable.
Okay, so it's
And
one
with respect to that,
sentence.
yeah, exactly. With
And
respect to
then
that,
it must be that that sentence in particular defines the validation ring inside K Laurent series. Because the Laurent series is one example.
indeed. Yeah.
So it would have to work. It would have to define the power series ring inside the Laurent series ring.
Absolutely.
Okay.
Absolutely. So as an example, we've seen, well, Blaise showed last week that ZP is existentially definable without parameters in Qt. Now, that's not an example exactly of that form, but fair enough, it's still interesting and related.
So I'm a little bit unclear on that notation. Is that F star the same as on the right? Because on the left it looks like it's F star and then FT? Or does that just mean if two elementarily equivalent fields have that means their power series rings are elementarily equivalent as well, right?
I'm not saying that. I'm saying that's a great question. I just mean that they share the same existential theory. And I'm not saying that's enough. Sorry, I was getting myself a little bit ahead there. Okay. But I'm just trying to say that we can start relating at this point. Let's just leave it as motivational. I mean, that's a true statement.
Yes.
But I don't want to say that that's in any kind of full argument or proof of anything yet.
Okay.
Yeah. I just wanted to say, one, we can start relating the theories of, or bits of the theories of these power series fields, given different models of the same complete theory, or indeed incomplete theory, of residue fields. And so at the moment, this is just I'm still motivating. Okay, so some examples. So this is kind of a super classical thing. I think normally it's conventional to write Robinson here. I seem to recall Philip reminding me at one point that this is not reasonable. Is that fair? Okay,
Which Robinson?
Julia. I mean,
Okay.
I think the point is it's much too trivial for that. I mean, it's not a hard formula at all. But anyway, it's a convention I feel the need to follow. And let's just start with a paper of Clucker's Dirac-Shahn, Linknet, and McIntyre, who investigated this kind of problem and proved several interesting theorems that are not exactly addressing what we're discussing here, but are still really, really interesting. And that is, they proved here there exists a uniform existential, no parameters, definition in a slightly adapted language, in the language of rings, where we allow one new predicate, which I'll just briefly call E2AS, but what is that? That's the image of x to the 2 minus x squared, x squared minus x is the image of that, There is a uniform existential zero definition in a blah 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 of all henselian valuation rings OV with finite or pseudo-finite residue fields. That's kind of massively generalizing this, well, not strictly generalizing because it's a different language, but it's sort of doing something like this, Robinson formula, but much more uniformly at the cost of introducing one extra predicate. You might observe that predicate is existentially definable, the subtlety being you need to use it in its negated form, so it's not just trivially an existential ring. And they also show, and this is not particularly hard, this is the second thing, 1, 2, there is no uniform E0L ring, or even universal zero L ring for that matter, definition of OV's valuation ring across all QP. Across all primes simultaneously. That's not terribly hard, that part. But it,
OV means ZP.
yeah, exactly. Yeah, of the henselian valuation rings across all these fields simultaneously. So, to some extent, they're honing in on what's the best thing you can say. To some extent. Okay. I want to give another example now, which is thinking about this type of field. So in this type of field, I will just credit making a Jochen, proving that there is an existential zero definition in L ring, but not uniformly, in no way uniformly, so no uniformity here. So, what's the idea? How does one actually do this? I won't repeat the formulas from last time that Blaise wrote down, but the rough idea.
So there is no uniform definition, or
That, yeah, but no uniformity. Yeah. And indeed, the fact that it cannot be done uniformly is basically the same point as made here. I wonder if they even state it like that. I don't think they do. The rough idea, and this is something that goes back to the paper called Topological Methods in the Theory of, no, it's not called that, it's called Model Theoretic Methods in the Theory of Topological Fields by Prestel and Ziegler, slightly corrected later by Prestel. There is a, if you let F be a separable, irreducible, nonlinear polynomial over a field K, where over a field little k, and then let KV be any henselian value field in the residue field little k, and let F hat just be any lift of F, just lift the coefficients. Yeah, that's right. Then the image of F hat evaluated on the whole field K also won't contain any zeros. So I'm allowed to look at the multiplicative inverses. Now that set is sufficiently sort of has interior. Do I mean that? Yes, I mean that. It really has interior. In particular, if you take two copies of it away from itself, one copy of it away from itself, you get everything in the maximal ideal. That's the maximal ideal of the valuation ring. OV, MV, OV, and it's also bounded, in particular, it's bounded by the valuation. So we get a really nice set here that's existentially definable, admittedly over, well, I've used coefficients that I've lifted from the residue field, so I need to be able to do that. So I'm just cheekily writing over little k. That's an existentially definable set. So I'm just saying there exists x, there exists y, such that my element is the difference of f at x inverse and f at y inverse, right? And then I've got everything around 0 in this nice big disk around it, but I'm not going too far away. So it's not very hard now, once you've got this, given that the residue field here is extremely not separately closed, it's not very hard to turn this into a definition of OV that's also existential and uses practically no parameters, because the parameters here are just 1 plus 1 plus 1 plus 1, so it's all defined over nothing. Bless you. And actually, it's also easy to get the other way around. Now, the proof I've outlined is a slightly shortened, compressed version that Arno came up with. So let me say something about that now.
So this minus means the set of all differences. It's not
Exactly,
it's
the
not-
set of all
It's not the set theoretic.
No, not the set theoretic. Sorry, I'm always in the habit of writing a slash for that.
Yeah, okay.
But it's a perfectly reasonable question, thank you.
First I was thinking of set theoretic, I'm trying to figure out what the difference between these two terms
These two
was.
identical
Couldn't
things.
find
Sorry.
it.
So in fact, we get that FQ square brackets T is E0 definable and A0 definable in FQ. That's for any Q of prime power, right? So, well, I mentioned Arno's name, Arno Fehm. So the kind of the second part of this story is I kind of read this paper and shortened the proof a little bit and did a more kind of uniform analysis and showed the following. Let F be a PAC field that doesn't contain, not containing the algebraic closure of its prime field. And I call its prime field FP, but you know.
What is a PAC field?
Pseudo-algebraically closed. I mean, it's existentially closed in every regular extension or every smooth. What do I mean to say? Every smooth curve over F has a rational point. So that FBPAC. But the important thing is, maybe I can just say, in particular, pseudo-finite fields are included here. And indeed, or finite, I mean, I can, or finite, for the FBPAC or finite, there is an existential formula with no parameters in our ring defining OV uniformly in any K V valued field henselian with residue field elementarily equivalent to F. So that's a much stronger uniform version of this thing, plus it works in other contexts, but it's also really uniform in that it doesn't matter what your value group is, it doesn't matter what else is going on in the valued field, right? Because we're outside of an Anscombe-Chernyshov context, so who knows what these theories depend on. So it's not just about power series fields, right? This is a much more general setting. And indeed, stronger than that, for every epsilon, there exists a formula which is also existential, 0 in our ring, which defining the OVs uniformly in any KV henselian with residue field FP, and I've missed a quantifier, there is a set P of primes of natural density 1 minus epsilon. basically, if you're prepared to throw away,
Probably at least one, that's excellent.
yeah, thank you. Density at least. Thank you. Yeah, so as long as you don't need to look at all primes, right, at once, you're good. As long as you don't look at all in this density limiting sense, you are good. Uniform from a uniformity perspective. So that's a very strong statement. All we knew before is that you couldn't do it uniformly for all p's, and now we know you can do it for most p's at the same time. Okay, I'm going to have to speed up a little bit. So I keep telling you the rest of the story. Well, so I still haven't told you what kind of property of the finite field, of a field, is that some or all of these henselian valuation rings are existentially definable in the language of rings without parameters. And the answer is remarkably clean, unlike this board. So, for an answer, we joined forces and applied a version of Beth's theorem, just as Blaise was talking about, using Beth's theorem. And, as it were, discovered the right condition. Now, the specific version of Beth's theorem we applied was kind of maybe, I don't know if it was well known, but anyway, let's say I learned of it from a paper of Alex Prestel, and I won't write it out explicitly for time reasons. I'll just tell you what it was that we isolated. So I'll write it as a theorem, and then I'll give you a definition after the theorem. Right. So, and let's just say it for one f now. So I'm just temporarily putting aside the uniformity issue. Okay, I just want to know what property of a field f it is that some or all of the valuation rings, as it were, over it are existentially defined. FP field. The following are equivalent. One, there exists an existential zero. Everything's going to be an L ring now. I only briefly mentioned that Glucker's direction link affect McIntyre thing. There exists an existential zero definition of OV in some K, which is equal characteristic non-trivially, well, V non-trivial henselian valuation V. Do I mean that? With residue field. Residue field F. So some particular equal characteristic non-trivial henselian valuation with residue field the right thing is existentially definable by some formula. That's one thing. There exists an existential zero definition of OV in all A any characteristic. Well, F's fixed, that's the residue field. So if we're in characteristic 0, I'm not saying anything interesting now, but if F has positive characteristic, that should be a bit surprising to you. Any characteristic, non-trivial, henselian, with residue field elementarily equivalent to F. Okay, so that's the kind of difference, the points of difference are here, right? So it's obvious that 2 is much stronger than 1.
So then it, oh, go ahead. Are you going to go to part 3?
There's going to be a part 3.
Oh, go ahead.
You want to say?
I was going to give my own part 3, but
Go on, please.
well, I mean, if it's true for all of these, then in particular, it would be true for the Laurent series field, right?
Yeah, that's true.
And that would imply 1.
Exactly.
So that, okay, that's my 3.
Perfect. What you said. But actually, my part 3 is a little bit different. But that's a great part 3. The part 3 I want to write down is the following: there exists no. Am I getting my? You can tell me if I get my alls, any's, sums, and every's mixed up. There exists no f star element to an extension of f, which admits non-trivial valuation v with, I like to write the residue field sometimes like this, f star v, that this residue field embeds into f star. Now, I'm really not saying anything about henselianity here. This is something that's happening between, let's say, copies of the residue field. It's happening somehow on or inside or between f stars, other versions of f, if you like. It's nothing to do with henselianity, it's just to do with a non-trivial valuation, and this is just sort of any embedding as a rule. Okay. So this is a strange condition.
Wait, doesn't this contradict what you're saying? There's no, why can't you just take the Laurent series?
There's no f star, an elementary, that's an elementary extension, which itself admits a non-trivial. I'm not talking about like f, this couldn't be f Laurent series.
Oh,
I mean,
yeah,
object.
sorry, I was confusing. Okay.
Yeah.
So that, okay.
So f is playing the role of the residue field, big K, some or all or any, most of the henselian valued fields with residue field, either f or something elementary equivalent to f. That's the game we're playing. Is that understandable? Well, this is a strange condition, but basically the answer, where does it come from? It comes exactly from a Beth theorem type analysis of the situation. Right, so I'm going to call it whatever. The precise version is from the present. So, and the point is, you discover it in much the same way that I sort of hinted at. It's possible to discover. I've rubbed it off, haven't I? To discover the not T henselian condition that Blaise was talking about. That I am not T henselian is a much weaker condition than this. But it is of the same kind, you might say. There are some remarks, right? There is a dual story. I don't mean that in a literal, strict sense. We never quite figured out the literal, strict sense in which it's a dual, but there's some kind of dual picture with universal definitions being exchanged for the property 3 prime, which says there exists no f star blah 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 with non-trivial henselian valuation on some subfield with E, the residue field of that, isomorphic to f star. That's just a different condition.
Does that mean that there's the same theorem except you have a 1' and a 2'?
In which E is exchanged for A. Exactly that. Exactly that. Now let me just draw a quick picture. Maybe, right? This property here, that's obviously the negation of a property. What's the property? Can I call this property embedded residue? Doesn't matter what you call it, but I just want to say, because I'm going to say that a few more times, let me now draw a picture of that. What is the picture? Well, for me the picture is this. You have F star, you have a place onto some residue field which lives inside F star again. That's just a picture. But what's the picture over here, where this property would be called something else? Let's call it, I don't know, Z large. There's a good reason for that, but let's not waste time on that. What's the picture? The picture is F star E something E plays onto F star. Okay? But this one should be henselian. Whereas the role that these diagrams play, actually it sort of falls out that this would be, it just fits into the rest of the diagram is to do with henselian valuations. But it's really somehow the one that appears here when you play this Beth game of building twisted examples. It needs to be henselian. So that's somehow where the henselianity disappears to. Never really fully understood that. Okay, that's just a kind of link between the two things. More remarks. This can also be stated for classes curly F of X, right? So we can think uniformly. And if you think uniformly, then 3 becomes there are no F1, F2 inside the class F with a non-trivial valuation Z, with F1 Z goes into F2. But then 2 gets strengthened, and it's then uniform over the sort of elementary closure of the class F. I'm not going to get into that now, I just want to say that this is a way of thinking about uniform definitions as well. You have to think about this kind of picture of valuations, this twisted little embedded residue property, but for the class, not for one field at a time. Another remark.
I don't understand what this bullet is saying. So what is can also be stated for classes?
Curly F of X.
So what does that mean? What is the statement then?
Okay, the statement is
You're going to give me analogs of 1, 2, and 3 for a family of F's.
Yeah.
So for example, what is 1 now say?
1 would be for everything, for every one would be I think I want to say for every F in the elementary closure of the class F, there's some K for which there exists a blah 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 blah. So characteristic is non-trivial, and the residue field should be elementarily equivalent to the F you started with. I mean, we can say stronger things, but that's the point. That's the weak condition.
The defining formula is uniform in the past. The defining formula is uniform in the
Not
past.
a priori.
Well, the strong statement 2 will then say this,
The
right?
strong statement, it follows, yeah. I mean, it doesn't, I mean...
So in the example of like FP, so what is contradicting 3? So if you take all the finite fields
if you want all the finite fields in one go,
Then 3 doesn't hold, right?
what's the problem with 3? All right, let me just write my third little remark, and then I'll explain the example.
Also in 3 you need to take somehow the dimension fast, otherwise this is a non-example.
Yeah, thank you. Yeah, thank you. Thank you. Can also state this for some parameters allowed, but from subfields that always live inside the residue fields. So I won't get into how one formalizes that, but roughly speaking, you can allow constant parameters, which in particular wouldn't take care of adding t to the language in the power series field case. Right. Okay, now I want to get into the examples and come to your question. So let's just sort of come back to the world of examples. Right. If we just take one FP at a time, it's clear that 3 is satisfied, right? Because there are no non-trivial valuations on FQ. Every model of the complete theory is isomorphic to FQ. Done. Okay. What about all FQs at once? All FQs. Well, now we do have method negation, because we can choose an ultra product.
You're talking about this 3 or that 3? You're talking about this 3 now.
This 3. Well, okay.
You're talking about
This 3. Okay. Let's call that curly F, curly F. Can choose an ultra product with, for example, algebraically closed algebraic part. And now it's absolutely possible to take a non-trivial valuation on F with algebraic residue field, and that, of course, can then be embedded back into itself. Okay. Again, it's the sledgehammer to crack the walnut that you can't find an existential definition uniformly, or even.
What is that? So the curly F bar? What does that mean?
I mean the elementary closure of the class. So this the class of models of the common theory of all the things in Australia.
Equivalently, everything that's elementarily equivalent to some ultra product.
Okay.
Let's discuss some more examples. So this example touches on a property of let's just stick with pseudo-finite fields. Well, it's a property of PAC fields actually, which is that any non-trivial valuation has algebraically closed residue field.
I'm a little confused by one thing. So you said that you can also, so you're going to restate this. There's an analog of this theorem for the class, for the curly F.
Yes, but I'm not going to state it.
Okay.
I mean,
So
I could, but I'm just I don't know.
Okay, so I don't know, okay, because if I take the naive analog of 1, then it seems to be true. So I was just wondering, maybe I don't have the right.
Yeah, so I said you need to then check it for every member of your elementary closure of the residue field. So it would be that for every
Also, 1 also refers to the.
that should
bar.
also be adaptive.
So it means that for every F in F bar, for every possible residue field in curly F bar, you would need to have this condition. Is that what you're saying?
Condition 1, yeah.
Yeah? Okay.
You forgot the switch.
Oh, I did forget to squidge it, thank you. All right, so I just said that every non-trivial valuation on a PAC field, or if you like, just on a, let's just think about pseudo-finite fields, has an algebraically closed residue field. It's a really interesting property, and it means that we just exploited the fact that a pseudo-finite field with an algebraically closed algebraic part does submit a non-trivial valuation and embeds back into itself. Well, the same is, well, the opposite is true in the other case, right? So, if f is PAC, pseudo-finite, maybe if you prefer, without algebraically closed algebraic part, then the negation of 3 holds. As in other language, F does not have embedded residue. Right? And this comes back to Fehm's result. Okay, now perhaps my favourite example, Q. So let's take now F is Q, and let's ask ourselves: does this have embedded residue or not? If you know the answer, don't answer. But if you don't know the answer, do you know the answer? It's a fun question. Okay. Well, so let's now let F star be some kind of proper elementary extension of F, which is Q. So, well, what do we know? We know that F star admits a unique ordering. A unique field ordering. Right? Unique ordering. Let's suppose there is a valuation V, non-trivial, with the residue field embedding back into F star itself. By the way, why does this submit a unique ordering? F already knows that every element of me is either sum of 4 squares or the multiplicative inverse, the additive inverse of the sum of 4 squares. Right? It already knows that in its L-ring theory. So suppose you've got a non-trivial valuation V on this thing, which goes into that. Then, well, you've got an ordering on F star that induces an ordering here, just by restricting it. And the way that orderings and valuations work tells you that that ordering lifts back to the other field. But we already know that field, which is F star, if you think of it as another copy of F star, also has a unique ordering. So what does this show? Then this shows that V is convex, valuation ring, if you like, is convex with respect to this unique ordering.
Why does the ordering induce an ordering of the residue field? You're
This
assuming
uses
is that the residue field, you're assuming it's a subfield.
into here.
Oh, so you're just restricting the order.
Exactly. That tells us there is some ordering here, and by Becquerel or however you want to think of it, you can lift that to an ordering of F star, but it must be the ordering of F star. So we now know that an arbitrary, any V with this property must have a convex must have a convex valuation with respect to that particular ordering. Our favourite ordering, the only one. That's all I'm saying. It's a little bit of a choice.
You mean you can always leave so that the residue field is convex?
Sorry?
You say there's always a way to leave the order in residue field so that the residue field is convex.
Yes. Exactly.
So how do you see that? I didn't quite see that.
How do you see it? I mean,
You have the ordering of the residue field, and then what do you do?
what do you do? I mean, this is the technology that goes into the Becquerel theorem.
I mean, basically, you need to additionally choose something about positivity of square classes. I mean, there's a choice involved. Basically, how like in F double brackets T, you need to, if you have an ordering on F, you need to decide is T positive or not. That's a decision you have to make. And once you've decided that, you get an ordering of the Laurent series field by looking at the initial
You
term.
can make one choice for every odd coset of the even of the even part of the value group, basically. Okay, but what does that tell us? I mean, all this is a bit. Why is that? What's the relevance here of this? Well, now we've got a convex. This is my little picture that I drew the other week. Now we've got this thing here. Let's just imagine that we were playing with Q star, and we just took the convex hull of Q, right, as our valuation ring. Just for the moment, let's just pretend that. Well, what's the maximal ideal? Well, that's exactly this infinitesimal subring, isn't it? And so quotienting by that exactly squishes together things that are infinitesimally close. So, and it's sort of the same even if you take a bigger valuation ring. In the residue field, right, so in OV mod MV, there is a square root of 2. Because, I mean, at least in this example you can see it directly, because Q already knows that it gets arbitrarily close to a square root of 2. So if there's anything in here, if there's anything here as an epsilon that tells you that you are at least that close in F star to a square root of 2, well, if we're quotienting by that means you found a square root of 2. Right, so building on this a little bit, what do we actually find? How am I doing time-wise? Oh, I'm well out of time. Sorry, gang. Okay. Well, that's on page 1. Okay. What is this? What does this tell you? This actually tells you that this residue field is real closed. Which is, I find, quite an amazing thing. It's not hard, but it's kind of surprising. For me, when I first learned this, it just was like coming out of nowhere. I didn't know that. And so in particular, does not embed back into F star, which already knows that it doesn't have the square root of 2. Okay, so that tells you that Q does not have embedded residue. And I'm out of time. But so let me just say, so Q double square brackets T is existentially 0 definable in Q double round brackets T. This is part of the story where we joined forces with Philip, and I just don't have time to explain anything except to say that theorem, the same is true. Same for any number field. And basically that's a similar technology. In fact, this is a rather small consequence of the things we ended up thinking about. But what I'm trying to say is that, in fact, if you start with any number field, you'll find some p valuation or ordering, or whatever you like, on it. And then one can check that the fact that that number field with respect to that valuation is dense in its p-adic closure. That fact is also preserved in elementary extensions. It's an elementary property, even though you're not allowed to explicitly name the valuation, right? Well, but there's this whole theory coming from Bjorn and Jochen and Jennifer and Philip and many other people about how to do this kind of thing, and going back further indeed. And so certainly that is an elementary property, and so therefore any elementary extension does not admit any non-trivial valuation, the residue field of which embeds back into it, because orderings and p-valuations share this property that when you induce them on subfields, suitable subfields, and then lift them back up, you still have an ordering p-valuation. So we end up with this, that's like the lifting question you were asking about. And then we get, by the denseness, we get the residue field should be closed in the suitable sense. But since no number field is closed in the suitable sense, neither real closed nor p-adically closed, contradiction. Okay? So the very end of that story is that k square brackets t is existentially zero definable in k double round brackets t. I'll stop there. Sorry for going over time.